In this section, I'd like to show you a proof by induction. We want to prove a given machine recognizes a given language. Let's run this with an example. This is the machine. It has two states, Q1 and Q2. Q1 is the start state, and Q2 is the end state, the accept state. From Q1, if I read a 0, I stay at Q1. If I read a 1, I go to Q2. And at Q2, if I read a 0, I go to Q1 and stay at Q2 if I read a 1. So this is the machine, only two states, 4 transitions. The language is S. S is the set of strings over the alphabet 0, 1. The strings should end in a 1. And our goal is to prove LM equals S. LM is the set of all strings accepted by M. This is the language defined by the machine. And if we want to show that LM equals S, a common way to show two sets are equal to each other is to show that one set is a subset of the other and vice versa. So we will use this strategy. First, we prove LM is a subset of S, which is the same to show if W is in LM, then W is also in S. Every member in this LM is also a member in this S. That's why this LM is a subset of S. Alright, that's our goal. So equivalently, we transfer that W in LM implies W in S to this statement. If I start from Q1, the start state, and I read a string W, if I end in Q2, an accept state, then that means W is in LM, right? So we use this as the premise. Go from Q1, the start state, reading the string, and in an accept state. If this is true, this implies this W ends in a 1. That means this W is in S. Let's call it P, the statement P. We want to prove this P by induction on the length of W. So the base case will be the smallest length of W, which is 0. So when the length of W is 0, W equals empty string. So we check, is this empty string going to end in this Q2? Is my premise true or false? So analyzing the machine, if I start from Q1 and I read epsilon, epsilon means nothing. If I read nothing, then I stay at Q1. And Q1 is not equal to Q2. So the premise of P is false. If the premise of P is false, then the whole statement P is true. So P holds for W. That's the base case. Now for the inductive hypothesis. I assume for all strings shorter than this W, this P holds, where W is a string longer than empty string. Now with this hypothesis, I want to do the inductive step. In this step, we want to show that this P holds for W. In the hypothesis, we assumed this P holds for all strings shorter than W. Now we want to show that this P holds for a longer string W. In this step, I need to use the hypothesis and analyze the machine to show that this will hold for W. Let's do it. Now this W is longer than empty string. We can write W as Vx, where V is any string over the alphabet and X is a single symbol in the alphabet. Since V is shorter than this W, by inductive hypothesis, we assumed this P holds for V. We might need to use this property, we might not, but that's what we have at hand. Now my goal is to prove that if I start from Q1, reading a string W ending in Q2, then this W should end in a 1. That's my goal. So we start with the if part, the premise. If the premise is true, I want to prove the conclusion is also true. Suppose the premise is true. Starting from Q1, reading the whole string W, the machine ends in Q2. Then I can replace this W with Vx. So from Q1, reading the string Vx, the machine ends in Q2. Now we analyze this machine. The only ways to land on Q2 by consuming a single symbol is by reading a 1 from Q1 or by reading a 1 from Q2. Those two cases. So we have, starting from Q1, if I only read V, then I can land on Q1 and X is equal to 1. This corresponds to the first case, reading a 1 from Q1. Or I have the second case, reading V from Q1 and end in Q2, then read another 1. So in both cases, this W ends in a 1 because this X is equal to 1 in both cases. So by now we have proved that the conclusion is true, given that the premise is true. That finishes the proof for this part. Now we prove the other direction. Remember, to prove two sets are equal to each other, we want to show that each set is a subset of the other one. Now we prove S is a subset of Ln. That means for any string in this S, this string need also be in this Ln. Equivalently, that means if W ends in a 1, that means W is in S. Then, if I start from Q1, the start state, and consume the whole string W, the machine should end in Q2, an accept state. That means this W is in Ln. Let's call this property P. And we want to prove this property by induction on the length of W. So in both directions, the patterns of the proof are the same. We only need to change the reasoning. Now first consider the base case. The base case considers the shortest length of W, which is 0. When W is 0, W equals empty string. Now we analyze, is this W in S? Does it end in a 1? Clearly, an empty string cannot end in a 1. So the premise of the property P is false. Thus, this P holds for W. If we have a property like if, then, this kind of format, if the premise is false, the if part is false, then the whole property is true. That's the base case. Now the inductive hypothesis. We assume for all strings shorter than W, this P holds for all those strings, where W is a string longer than empty string. Now let's check the major part, the inductive step. In this step, we want to show that this P holds for W. Our goal is to show that if this W ends in a 1, I also want to show that this W ends in Q1. I also want to show that this machine ends in Q2 when running on W. So we start with the condition of W. The length of W is greater than or equal to 1. So we can write W as Vx. V is any string over this alphabet, and X is a single symbol in this alphabet. X is either 0 or 1. Since this V is shorter than W, the inductive hypothesis holds for this V. So the property P is true for V. Now we want to prove this P holds for W. What we do is we assume the premise is true for W, and then we prove the conclusion is true for W. So we suppose W ends in a 1. Then this X is equal to 1 because W equals Vx. Now we consider two cases for V. Case 1 is V ends in a 1. So by inductive hypothesis, when the machine reads this V, it should end in Q2. In this case, if I read the whole string W, that means I can go from where the machine ends on V and read one more symbol X. That's the transition. So starting from Q1, I'll read the whole string W, which is equal to say, starting from Q1, I'll read the whole string Vx. This is equal to I read V first, and from where the machine ends on V, I'll read another symbol X. The machine ends in Q2 after reading V. So starting from Q2, reading the symbol X, X is equal to 1, right? So the machine will end in Q2. So by this, we have shown that if W ends in a 1, then starting from Q1, reading this W, the machine ends in Q2. So P holds for W in this case. Now let's consider another case. V does not end in a 1. In this case, the machine can either end in Q1 or Q2 after reading this V. Because in this case, the premise is false for V. V does not end in a 1. So we don't know if the conclusion is true or false for V. So we analyze both cases, both situations. If the machine ends in Q1, then reading the whole string W is equivalent to read first V, then read X. After reading V, the machine ends in Q1, and reading one more 1, which is X, the machine goes to Q2. So in this case, the machine will end in Q2 after reading W. In this case, P holds for W because we have shown that if W ends in a 1, then the machine will end in Q2 after reading W. Now let's consider the other case. After reading V, the machine ends in Q2. So in this case, if I want to read the whole string W, I start from Q1. Then I'll replace W with Vx. So the machine will first read V, and then from where the machine ends on V, read another symbol X. So the machine ends in Q2. From there, if I read one more 1, the machine stays at Q2. So in this case, after reading the whole string W, the machine ends in Q2. In this case, I have also shown that suppose W ends in a 1, then the machine ends in Q2 after reading W. That means the property P holds for W. In all these cases, I have shown that if the premise is true, then the conclusion is true. So the property is true for W. In the inductive step, we have a property to prove, which is of a format if, then. So we always start from the if part. We assume the if part is true. We then lead to the conclusion. We show that the conclusion is also true. I want to draw your attention for case 2. In this case, we know this property P holds for V. That means if V ends in a 1, then this machine will end in Q2 after reading V. This whole property is true. But if the premise of this property is false, then we don't know if the conclusion is true or not. So in this case, if V does not end in a 1, we don't know if this machine is going to end in Q1 or Q2 after reading V. For case 1 and case 2 in the whole, we analyze these two cases because we only know this property P is true for V. But we don't know if it's true because of case 1 or if it's true because of case 2. So we need to analyze both cases. So that's the end of the proof. For a general proof by induction, you always show these three parts: the base case, the inductive hypothesis, inductive step,